All right, let's dive right into this explainer. Today, we're exploring an absolutely fascinating intersection where civil engineering is borrowing some serious tricks straight from biology. We're looking at a future where our built environment doesn't just sit there degrading over time, but actually actively fights its own decay. Welcome to the era of self-healing concrete.
So, to really grasp why this is such a massive game changer, we first got to ask ourselves a pretty simple question. What is the actual biggest threat to our concrete infrastructure? You might immediately think of, heavy loads, massive impacts, maybe even earthquakes bringing down giant structures. But honestly, the true enemy is entirely invisible to the naked eye.
The real battle for structural integrity happens at the microscopic level. It's all about the microcrack. Even tiny hairline fractures, which are totally inevitable in standard concrete, by the way, allow water to slowly, quietly seep in. That water eventually reaches the internal steel rebar, and it causes it to rust. And what happens when rust expands? It literally blows the concrete apart from the inside out. It's a slow, quiet, but absolute structural failure. Self-healing concrete is designed to stop this at the micro level long before it ever becomes a real problem.
To put the sheer scale of this problem into perspective, consider this stat. According to life cycle assessment data, in the UK alone, repair and maintenance account for almost 45% of all expenditure in the entire construction industry. We are talking about spending billions every single year just patching up decay. It's a massive economic and environmental burden.
Moving into Section 1, Bacteria to the Rescue. Biology meets engineering. Let's see how we're actually tackling this. Now, standard cement does have a natural but very limited ability to heal tiny cracks through a process called autogenesis healing. It's basically just ongoing hydration. But to truly fix this decay problem at scale, scientists are engineering autonomous healing systems. These are advanced bioengineered systems embedded directly into the concrete that sit completely dormant until damage occurs, and then act entirely independently to repair the structure. This is where the biology comes in, and it's so cool. It's a clean, biological chemical reaction. During the mixing phase, dormant bacteria and a calcium lactate food source are added right into the concrete. Later on, when a microcrack forms and water inevitably enters, that water wakes up these dormant Bacillus subtilis bacteria. Once they activate, they feed, they consume oxygen, and they excrete calcium carbonate, which is limestone. This calcite completely fills the crack, sealing it up and stopping the water dead in its tracks. It's a chemical reaction performed entirely by life. Now, you might be wondering, why this specific Bacillus strain? Well, concrete is a highly alkaline, toxic, and incredibly pressurized environment. Most life simply wouldn't survive. But these specific bacteria are chosen because they have this unique ability to form incredibly tough spores. That armor protects them from the intense mechanical pressures of mixing and the harsh pH of the concrete, allowing them to just wait patiently for years until a crack finally wakes them up. Which brings us to Section 2, Engineered Delivery Systems. Basically, how on earth do we package life inside solid stone? So, how do we physically pack these microscopic healers into a massive poured wall without just crushing them? The leading method right now is microencapsulation. These tiny capsules are often made with a super tough melamine formaldehyde shell, or they're embedded in expanded clay. When you mix it into a fluid batch, it just looks like normal concrete. But that shell's entire job is to protect the healing agents inside until a propagating crack physically breaks the shell open. When it snaps, it releases the healer exactly where it's needed most. But researchers at Cambridge are pushing this to a whole new, futuristic level with biomimetic vascular networks. Picture a cutaway of a concrete wall. But instead of just solid stone, imagine a 3D printed network of hollow veins running all through it. Inspired by human skin and tree leaves and utilizing Murray's law for optimal fluid transfer, these channels can literally pump healing agents, like sodium silicate, directly to the location of a crack. We are literally giving concrete a circulatory system. All right, let's jump into Section 3, the engineering reality check. Time to look at the limitations and constraints. Let's pause the futuristic hype for a second and look at the real-world engineering hurdles, because it's not totally perfect yet. First off, survival. The highly alkaline pH 12 to 13 environment of concrete is toxic, which means we have to use that expensive microencapsulation process. Second is strength. If you replace solid aggregate with hollow capsules, you're fundamentally altering the mix. If it's not designed perfectly, you can actually see a 5 to 8% reduction in compressive strength. And finally, cost. Cultivating bacteria and producing calcium lactate is pricey. The initial material cost is effectively double what you'd pay for standard concrete.
Because of these constraints, especially that price tag, self-healing concrete is currently very much a premium product. It's not going to be used for your typical suburban driveway anytime soon. Instead, it's being deployed for highly critical infrastructure. We're talking offshore marine rigs constantly battered by saltwater, deep bridge foundations, massive tunnels, and underground nuclear waste facilities. Places where sending a crew down with a bucket of patch cement is either completely impossible or wildly dangerous.
Moving on to our final section, self-maintaining infrastructure, a sustainable paradigm shift. If you visualize the lifespan of concrete on a graph, traditional concrete is just a steady, depressing downward curve. In fact, 10% of structures fail within just 10 years, and standard patch repairs can consume up to 50% of the original concrete volume over a 50-year lifespan. It's incredibly wasteful. But self-healing concrete creates this awesome sawtooth structural recovery graph. Every time a microcrack forms, the strength drops slightly, sure, but then the bacteria heal it and the integrity spikes right back up. It continuously intercepts decay before it ever escalates into a structural failure. And guys, this has absolutely profound implications for our planet. When you consider that concrete production alone accounts for a staggering 8% of all global anthropogenic greenhouse gas emissions, autonomously extending its lifespan is a massive leap forward. By eliminating the need for constant patch repairs and endless rebuilding, the lifetime carbon footprint of a structure drops dramatically. We are literally witnessing a fundamental shift in civil engineering. Think about it. Just as software engineers now write self-healing code that actively patches its own bugs, we're building a self-maintaining infrastructure movement. We're creating materials that actively fight their own decay. It leaves us with a pretty fascinating final thought. As we fully enter this era, what other lifeless, static parts of our physical world will soon wake up and heal themselves? Thanks for joining us for this explainer, and keep questioning the world around you.